Good evening, everyone. This is the session number 5 from the playlist of alternating current. The topic is AC voltage connected to an inductor, and here I have drawn one simple diagram in which one inductor of self-inductance L is connected to an AC source. So here the voltage across this AC source is given by V is equal to Vm sin omega t, where Vm is the amplitude of the oscillating potential difference and omega is the angular frequency. So this is now a pure inductive circuit, and here I have considered that the resistance of this inductor is negligible. In the market, however, these inductors, they have got appreciable resistance also, but in this case I have assumed that this inductor has got negligible resistance. So now again one more thing, these inductors, what is an inductor? So inductor is basically a passive component which is used in the electrical and the electronic circuits to store the energy in the form of magnetic field when the current passes through it. And these inductors are have got a variety of uses, and these inductors are basically used in the electrical and the electronic these circuits. Some of the uses are that they are used in the tuning circuit to get a desired frequency. They are also used as the proximity sensors, relays. They are also used as filters and choke. And in the market, they are normally sold by the name of the choke, coil and the reactors. So this is a brief description about the inductor, and so today we will be discussing about the phase relationship between the voltage and the current in the case of a pure inductive circuit. So this is a pure inductive circuit, and here I have assumed that this inductor does not has any resistance. However, in reality, the inductors do have appreciable amount of resistance within themselves. So first thing is that using the Kirchhoff laws, Kirchhoff loop rule and the Lenz law, we can say that we as per this Kirchhoff law, the potential this difference across all the elements in a loop is equal to 0. So V is the potential difference across this AC source, and L di upon dt is the potential difference across this inductor, and this minus sign has come from the Lenz law. So V minus L di upon dt is equal to 0. Now from this equation I am getting what? This di upon dt will be equal to V upon L. Now V is equal to Vm sin omega t, and divided by L, V is equal to Vm sin omega t divided by L. Now in order to find the current in this circuit, what I have done is, what I will be doing is that I will be integrating this equation with respect to time. So I have integrated this equation with respect to the time. So what I will be getting here is that this I will be equal to integration of Vm sin omega t upon L. Now Vm upon L is a constant, so I have taken it outside, and so I have to only integrate this sin omega t. So the integration of sin omega t will be equal to minus cos omega t. So final plus I will be getting the this is a constant, so this is a constant of integration. Now this constant will be having 0 value because there is no time independent component of the current. So this would be equal to 0, and now so what I will be getting here is from this equation, that is I is equal to minus Vm divided by omega L, this cos omega t plus the constant of integration, which will be equal to 0 because there is no time independent component of the current. So this will be equal. So finally what I am getting is I is equal to minus Vm divided by omega L cos omega t. This equation means we have got this equation after integrating this sin omega t. If you integrate this sin omega t, you will be getting minus cos omega t divided by omega. So now from this equation from this equation, I can just convert this equation as Vm upon omega L. This minus sine omega t can be written as sine omega t minus pi by 2. Okay, so now here this omega L is very similar to the resistance in a this resistive circuit, and this is called omega L is called the inductive reactance, and this is very similar to the resistance in the resistive circuit. So this is called inductive reactance. Now, so what I can write here is that I will be equal to Vm and divided by this omega L, and omega L is basically represented as XL. XL is what? This is the inductive reactance, and I can write this as sine omega t minus pi by 2. Now this Vm upon XL is equal to Im, where Im is the amplitude of this oscillating current. So this is equal to Im sine, or I will be writing it here. So this is equal to I is equal to Vm upon XL is equal to Im, where Im is the amplitude of the oscillating current, and this is equal to In sine omega t minus pi by 2. So from here we can see here that this current is lagging the voltage by pi by 2. Okay? So in the pure resistive circuit, we know that the voltage and the current, they are in the same phase, but in this case, in the case of a pure inductive circuit, the current is lagging the voltage by pi by 2. So this is the relation which I wanted to derive in this session, and I just wanted to prove that the current is lagging the voltage by pi by 2 in the case of a pure inductive circuit, and I is equal to Im sine omega t minus pi by 2, and here the voltage, or can say the potential difference across this AC source is equal to Vm sine omega t. Okay, so if I want to calculate the instantaneous power, so that can also be calculated with the help of these two equations. So instantaneous power will be equal to power that is instantaneous. This is equal to Vi, and this will be equal to Im Vm into sine omega t minus pi by 2 sine omega t. So this is the instantaneous power which has been obtained by multiplying the value of V and I from the equation number 1 and 2. So thank you very much for joining in this session. In the next session, I will be coming up with a very simple question which will be based on this topic of this topic, that is AC voltage across an inductor. So till then, have a nice day. Bye.